Okay, we are going to, as we talked about last time, we're going to go ahead here to chapter 6, the last part of 4. Chapter 4 is up there and posted, um, involving electron configuration, periodic trends. A reminder that we are skipping chapter 5, so we're not going to do 5 at all, which I think should be nuclear chemistry, so no 5. So we're just going to go off to 6 here. This obviously is exam 2 material that we're starting right now. So, and exam 1, as you hopefully saw from announcement, has been moved to 1 week from today. Will not be moved again. Yes, so we would definitely be doing it 1 week from today in lecture. All right, so in this chapter, we're going to talk about two kind of really important type of things or topics. We're going to talk about nomenclature, which is how to name everything. And then we're going to also talk about bonding, which is how to draw everything as well. So there's a lot sort of packed into this chapter. And we're going to get into it, even though it does say chemical bonds. We're going to actually start with nomenclature and naming. And a reminder, I think, in the previous chapter and a couple of those chapters previously, we talked about ions. And remember, ions are things that have charges. And there's two types of ions that we talked about. And I think specifically we sort of talked about it when we are doing like how many protons, electrons, and neutrons something has. And if it has a charge, sort of what changes. And remember that there are cations, which are positively charged ions. They are usually achieved by losing electrons. So remember that when you lose electrons, you have more protons than negatively charged electrons, so you become more positive. And typically, the elements that do that are metals. And typically, metals are the ones that will do that for some of the reasons that was discussed at the very end of the previous chapter there when we talked about periodic trends. They have low ionization energy, they have low electronegativity. Frankly, they're just like, take my electrons. I don't really care. Go ahead. They're not really looking to hang on to all their electrons or attract electrons. Anions, on the other hand, are again negatively charged ions. That's a result of gaining electrons. And typically, nonmetals are the ones that do that as well. And when you gain electrons, you have more negatively charged electrons than you do positively charged protons. So you become more negative as you gain electrons. Nonmetals, which again is the upper right-hand side of the periodic table above the staircase there, they are the ones that typically will gain electrons. Again, for those periodic trends in the end of the last chapter, where nonmetals have all the properties of they definitely want to hang on to their electrons. And in addition to that, nonmetals also like to bring electrons towards themselves. So they like to attract electrons to themselves. So that is really the basis of two types of bonds that we'll talk about here, both in nomenclature and bonding. And one type of sort of situation, as we'll talk about, is an ionic bond. And an ionic bond is between a metal and a nonmetal. And what happens is because they have all those kind of different periodic trends, as I mentioned before, metals are pretty much, go ahead, you can take my electrons, I don't care that much. Non-metals are like, thank you very much, I will take your electrons because I like to like gain electrons. We end up getting a transfer of electrons. And we get this transfer of electrons from the metal to the non-metal. And that's what creates a cation that's positively charged for our metal. And that creates an anion that is negatively charged for our nonmetal. And that is the attraction that holds that bond together. So in an ionic bond or an ionic compound, there is the what is referred to as electrostatic attraction, which is basically the attraction between positive and negative that holds that together. One of the things that you should understand, and you'll talk obviously a lot more about as we go through this chapter, is there's absolutely no sharing of electrons in an ionic bond. So when we have an ionic bond, we have no sharing of electrons. The other type of bond that we'll talk about both in nomenclature and in bonding is covalent bonding, and that is typically between two nonmetals. So what happens when you get kind of two nonmetals together is, unlike the very difference that there is in the periodic trends between metals and nonmetals, when you get two nonmetals together, because they are all both in the same spot on the periodic table, essentially, they both want to hang on to their electrons, and neither one of them really wants to get rid of their electrons, and they both want to bring electrons towards themselves. So what happens is when they get together, the best that they could agree upon when they have that conversation is, I'm not going to get rid of my electrons, you don't get rid of your electrons. How about we just share the electrons? So in a covalent bond, when we have two nonmetals together, they decide to share electrons after that exact conversation occurs. And as we will talk about later on in this chapter, sometimes the sharing is equally sharing, and sometimes the sharing is unequal sharing. But the difference between a covalent bond is, again, in a covalent bond, we have sharing of electrons. In an ionic bond, we have no sharing of electrons. A transfer of electron has basically occurred. Now, regardless of what type of bonding that we're going to talk about, the ultimate goal of all of bonding, both ionic bonding and covalent bonding, is actually a very simple goal. The goal of all bonding is for everybody in the bond to achieve noble gas configuration. And what we're talking about is their electron configuration. So the purpose of all bonding is for everybody to basically end up just like the noble gases in terms of their electrons. The reason that is, as we talked about the periodic table. Noble gases are chemically inert, they're super stable, and that is the goal of everybody when they're trying to make a bond, is to get to a more stable situation. And the way they could do that, as we will see as we go through this chapter, the way they could do that is by either transferring electrons in the case of an ionic bond, gaining and losing, or sharing electrons. Allows everybody within a bond to basically achieve that really, really stable electron configuration, just like the noble gases. As we'll talk about, it's important to also remember that they don't become noble gases when they bond. They just have the same electron configuration as noble gases. They're still the same elements because the protons don't change, right? As we talked about, protons is what determines what element it is. So when we bond, it only involves electrons. Protons stay the same, all elements stay the same, but how the element changes is their electron arrangement now lines up with how a noble gas's electron arrangement is, and they now become very, very stable in that situation. All right, so that's a little preview of sort of bonding and also a little bit of nomenclature. Before we get too far into it, let's come back here to the periodic table I have somewhat drawn here. We'll just put in some more groups here. 6, we'll go 5. Go 4. Good thing I made a big one here. We'll go 3, and we'll go over here. We'll go 2, and we'll go 1. Now, as we talked about as well, I think the other day, elements on the periodic table, when they are by themselves and not combined with anything else, they do not have charges. Really, as we will see here, things only get charges in an ionic bond situation when metals and nonmetals come together. That's actually when they do gain charges. But when things do gain charges, there are, again, certain elements on the periodic table that have fixed positive charges. And when you look at the periodic table, everybody in group 1, the metals, will make a +1 charge when they actually do make a charge. Everybody in group 2 will make a +2 charge. Over to group 3, for the most part, it's going to be aluminum is pretty much the element that you're going to kind of really see the most. Sometimes gallium's included, which is right below it, but usually it's aluminum. And aluminum will make a +3 charge. Right around here, that's boron up there up on top, and we got that kind of staircase kind of coming through here. And we kind of skipped group number 4 because you kind of got some nonmetals on top, some metals on the bottom, some metalloids in the middle. Starting at group number 5 in the nonmetal region, which is above the staircase, we have guys that will make -3, like nitrogen and phosphorus. Group 6 will make -2, like oxygen, sulfur, and selenium. Group 7 will make -1, bromine, chlorine, fluorine, all those guys there, iodine. So it's kind of like 1, 2, 3 positives, skip, go backwards, 3, 2, 1 negatives. Once again, these are metals on this side, which should be positive. Up here is our non-metals, right, which should be negative as you go through there. Right here's our transition metals, and our transition metals, as we will talk about here in this chapter, one of the characteristics of transition metals is they can have a variable positive charge. So in some cases, for example, copper could be +1 charge, and in other cases, copper could be like a +2 charge. So it kind of depends on the situation. They don't have a fixed positive charge. There are only 3 transition metals that have a fixed positive charge, and that is up here in the zincage range, right below it at cadmium, and hang a left over there to silver. Zinc and cadmium will make a +2 charge, and silver will make a +1 charge. So those 3 transition metals are sort of exceptions. They will have a fixed positive charge no matter what the situation is. And again, it's basically zinc and cadmium +2, hang a left, that's cadmium, and you'll have a +1 for silver. Everybody else in the transition metal region, and also in this area of the periodic table, which is not necessarily transition metals, but areas where you find things like, I can find what I want right there. There you go. There you go. Try that. Over in this sort of area, where you'll find things like lead, tin, antimony, bismuth, etc. Although they are technically not transition metals, they are still metals because they're below the staircase. And they also have a variable charge. So they can make different types of charges, like lead, which is Pb, could have a +2 charge in certain situations, a +4 charge in certain situations. So the transition metals, and then just to the right, underneath the staircase, those metals are also basically named the same way as transition metals because they can have a variable type of charge. Any questions on that there? Okay. All right, so let's talk about nomenclature. And again, as I mentioned before, that's a fancy way of saying naming things. And let's just talk about a few things, which is there are certain compounds that go by just sort of common names. I would say definitely these here for sure. H2O is not a trick question. It is water, yes, and you should put water on the exam or quiz when it shows up, and you should not put weird names like nobody wants a refreshing glass of dihydrogen monoxide, right? Because that probably is not going to sell very well in the store. So it is water, H2O. NH3 is ammonia, and it should not be confused with something we will see later on, which is an ion that looks very, very similar to it. CH4 is the simplest organic molecule you could have, and we definitely will see him later on in the organic chapters. I'll be honest with you, most people still call NaCl sodium chloride, and has some table sugar happening there. So I would say those 3 that are circled, definitely you should know those. So when we talk about ions in general, as we talked about, we have our cations, which are positively charged. We have our anions, which are negatively charged. And if you have just the ion by itself, say you have H plus, or you have Na plus, or you have Ca2 plus. First off, these are the formulas of the ions. If it is an ion or a cation by itself, you do have to include the charge. Otherwise, it's not an ion. So you do have to have like the +1 up there, the +1, the +2. That does need to be written. When we have positive ions and we want to name it in just the ion by itself, for the positive guys, we simply just use the element name. So H is hydrogen. This would be known as the hydrogen ion. Na plus, Na is sodium. This would be known as the sodium ion. Ca2 plus, that's going to be our calcium ion. So if you have any positive ion by itself and you have to write the formula for it, it should obviously have the charge associated with it, and it should basically just use the whole name of the element and put ion at the end. Negative guys are a little bit different in terms of how we name those ions. So if we have something like H minus or O2 minus or N3 minus, these are anions. Again, they have the negative charge. Now, the difference here, though, when we name it is we will use part of the element name, and then we'll kind of drop the last part of it, and sometimes a little bit more than the last part of it. And so we kind of use the base of the name, and we drop the last part, and we replace the last part with IDE. So if it's a negatively charged ion, you take the element name, drop the last part, put IDE. Instead of hydrogen, this becomes the hydride, IDE, ion. Instead of oxygen, this becomes the oxide ion. Instead of nitrogen, this becomes the nitride ion. You had Br minus. Instead of bromine, this would be bromide ion. So each of these guys will end in IDE. That tells you basically it's a negative ion. And again, take a little bit of the front part of the name. In some cases, we get rid of a lot of the front part, but the basis of the name. As you also see here, we do have an interesting thing that sort of happens, and it is with hydrogen, which is sort of a little special element. It is the only element that could kind of go both ways. It could be positive and it can be negative. I would say in most cases, hydrogen will be positive. The only time it will be negative is if it comes after a metal. So if you have it after a metal, it'll be the negative version of it. But most of the time, it's probably going to be positive. And it really is the only element that can kind of do both things, positive and negative. Now, another really important thing, as we'll talk about here, is when we put ions together, they do need to come together. The positive ion and the negative ion, they need to come together to equal no charge. So all the positive charge ion and all the negative part of the ions, when they come together, they need to come together in the simplest way that will get you zero. So for example, obviously here, if I have sodium, which is +1, and I want to put that together with chloride, which is -1, obviously when I take +1 and -1, it adds up to 0. So the proper formula for this would be NaCl. That is the formula for the ionic compound. The formula for the ionic compound has no charge. It has to equal 0. And again, it has to be the simplest way you can get to 0. There's many ways to get to 0. It's got to be the simplest way to get it to 0. So one of the interesting things about ionic compounds is the formula will not have charges, but it is made up actually of two things that do have charges. So when we see the sodium here in the formula, it really is representing the sodium with a charge. And when we see the Cl in the formula, even though there's no charge in the formula, it is representing the chloride ion that does have a charge. Any questions on that now? Now, if I took my sodium ion and I hooked it up there with my oxide ion right there, when I put these together, will it add up to 0 if I take +1 and -2? It will not. In this case, we actually need more of which one? We need more of the sodium, right? We actually need not one, but we need two of them, right? That gives you a +1 and a +1. So our positive charge now is +2 overall, and our negative charge is -2, and that's going to equal 0. And when we write our formula, we would just count what we did there, which is I have 1 sodium, 2 sodiums, and we write Na with a 2 on the bottom. Remember that the little 2 or the little number there goes to the element to the left. So that 2 represents that there's 2 sodium ions present. And there's only one of these oxygens. And that would mean we would just put the 1O there. Much like in chemistry, we usually don't write the 1. So if you don't see anything written there, it basically means that there's 1 basically there. We usually don't write the 1 if there's nothing there. So, and that would give us 2,0. And that would be the proper formula here for sodium oxide. The reason this has to happen like this, that when you take a positive ion and a negative ion and put them together to equal 0 in the simplest way possible, it actually has to do with the bonding aspect of it that we'll talk about a little bit later on. But we already sort of talked about it, which is what that allows everybody in this ionic compound to achieve is that noble gas configuration, just like the noble gases. So, for example, all 3 of those ions, the sodium ion, both of them, and the oxygen ion, they all, by coming together in that fashion, all 3 of those things will then end up with an electron configuration like you see in noble gases, making it super, super stable. And same thing down there with the sodium ion and the chloride ion. Just by needing one of each of those, that's going to allow both of those ions again to reach that electron configuration like we see for the noble gases. Any questions on that there? All right, so I got a little bit of that along the way here, and I definitely wrote over everything there. So let's just kind of erase. There you go. All right, so as we're going to talk about here, we're going to talk about naming binary compounds. Binary compounds means there's kind of 2 things together, or 2 elements together. There's basically 2 classes of compounds. As I mentioned at the start here, if you have a metal and a non-metal together, you shouldn't think twice about it, yes? That's an automatic ionic compound, ionic bond happening. If you get those 2 guys together, a metal and a non-metal, 100% of the time, just write ionic. If that's the question of what type of bond it is, it's always going to be that. Just like if you get 2 non-metals come together, because of those periodic characteristics, you're always going to get a covalent bond. And sometimes these are referred to as molecular compounds. Sometimes people will refer to the compound as a molecular compound. Again, the main difference, as we'll talk about when we get into bonding, as we talked about earlier, is a transfer of electrons here. And down here we have sharing of electrons. So again, that is the main difference between those. And as I mentioned earlier, and as we will see later on, again, by sharing electrons in a covalent bond, that also is allowing everybody to get to that noble gas configuration and group number 8. All right. Oops. So when we write a ionic compound formula, in addition to making sure that it equals 0, the sort of format for it is always the cation that comes first, so always the positive guy, then the anion. And that is always the formula for both, actually, the formula and the name. So when you're naming an ionic compound or you're writing the formula for an ionic compound, that is the deal. You want to always go the positive guy first, followed by the negative guy, the cation and the anion. Basically, the metal first and then the non-metal, except for hydrogen, which we can play into here. As I mentioned before, to name those ions, we simply just name the element in that case if it's a cation. Now, when we talk about ionic compounds, it's sort of broken up into a couple of categories, and both of these, type 1 and type 2, are ionic compounds. So again, as I mentioned a second ago, when we see ionic, we jump right into, I got a metal and a non-metal involved. And because of that, I should be thinking in my head, we're going to get a transfer of electrons from the metal to the non-metal. That's what's going to generate our ions that are present here. Again, the cation from the metal, the anion from the non-metal. So again, that is what's going to generate those ions. And that's really why elements don't have charges until they come together. When they come together in this situation, that is when they're going to gain these charges. Now, what is the difference between type 1 and type 2? I'll put it this way. Whenever you have a metal involved, in naming, it's the most important thing. So the metal is always the thing that you want to look at when you have to name something. And a type 1 compound, the metal has a fixed charge. So if you remember, as we talked about at the beginning here, on the periodic table, the groups that have fixed positive charges are metals in group number 1, group number 2, group number 3, which is aluminum, and also our 3 sort of transition metal exceptions, zinc, cadmium, and silver. So if you have a formula given to you or even a name given to you, and it's an ionic compound, and as soon as you recognize the metal as being either from group 1, group 2, or group 3, or it's zinc, cadmium, silver, just go, cool, I'm in a type 1 situation. And we'll talk about what that means in just a second. But that's what you want to look at, is always the metal. Type 2 compounds is where the metal, which again is the most important thing, can make a variable charge. So if you have a type 2 ionic compound, that metal can make a variable positive charge. And if you remember from what we talked about at the beginning, that's going to be your transition metals, except for those 3 that's above, zinc, cadmium, or silver. And just to the right, as we talked about below the staircase, things like lead, tin, etc., that area of the periodic table. When you see a metal like that, what that should put in your head is it's a type 2 compound. And again, there's a different way we have to name type 2 than say type 1 compound. So you want to first, when you come across something that maybe is a formula and you want to name it, you should really start with sort of an identification sort of list. You want to look at the 2 things and go, what do I have there? Do I have a metal and a non-metal? Do I have 2 non-metals? The answer is you have a metal and a non-metal. That should tick the I'm in an ionic situation here. Then you want to go metals involved. I want to look at the metal and see where it is on the periodic table. If it's in group 1, 2, or 3, zinc, cadmium, or silver, it's a type 1. If it's not, then it's going to be a type 2. So that's a process you want to kind of go through when you look at something to sort of identify it. As you can see here, chromium, for example, in certain situations can be +2 or +3. Copper, as I mentioned earlier, could be +1 or +2. So because they have a variable charge, as we will talk about, there's pretty much just an additional sort of thing you have to do when you go to name those guys. Here's a table from your book of just ions by themselves. And as we talked about before, everybody that's positively charged, we're pretty much just using the element name like it comes. And then here's all of our negative guys, which have the IDE at the end of it. And again, that's going to be kind of like your group 5, 6, 7 on the periodic table. Your -3, -2, -1, going from 5, 6, and 7. That way will get you the charges. All right, so let's talk about type 1 compounds and how to name them. Again, type 1 compounds, ionic. It's their metal and non-metal together. And once again, as I mentioned, always the metal is the most important thing. So basically, if we take one that we saw earlier, NaCl, when I look at this, I go, sodium is a metal. Cl, which is chlorine, is a non-metal. And again, that's going to tell me we are dealing with an ionic compound. I would then want to look at the metal, which is sodium. I would want to go to the periodic table, and on the periodic table, you will find sodium hanging out there in group 1 on the periodic table. And because it's in group 1 on the periodic table, it's going to tell you that it has a fixed positive charge, which tells you it is a type 1 metal. And once you've basically figured out those 2 things for type 1 compounds, that's all you need. You don't have to figure out anything else. You just got to follow the rules for naming it. So the way that we name a type 1 compound is we use the whole name of the metal, the positive guy. And the nonmetal gets the IDE treatment at the end. That's it. So if I come back to my NaCl and I do my little thought process there, as soon as I see it's type 1, it's ionic, I'm just going to go here and go Na is sodium. So I'm just going to write the whole entire name. And the Cl goes from chlorine to chloride, IDE at the end. And that would be my name, sodium chloride in that case. That's it. I don't have to figure out anything else or anything like that. Now, if we take a look at the other one that we kind of saw there, was like Na2O, right? So when I look at this, I would go through the same sort of situation. I would see sodium is a metal. Oxygen is a nonmetal, so that tells me once again we are in the ionic compound. I would look at the metal, which is sodium. Once again, it is group number 1, which means it is a type 1. At that point, once again, I don't have to do anything else here. So the whole name of Na is still sodium. And oxygen, which is the nonmetal, is the oxide and gets the IDE treatment. So this would be sodium oxide. This would not be disodium oxide because it sounds more chemistry-like. Yes, that's a little chemistry up and put some prefixes. That doesn't give you the right answer. That gives you an X over your answer. Yes, because that is not the place. So there is absolutely, positively no prefixes involved in type 1 naming, and you should not use them. It doesn't matter if you got 2 sodiums like I do there, you got 40 sodiums, you got 30 oxygens, it doesn't matter. That is how you name it. Whole name of the first guy, the positive guy, ID on the second, has no bearing on the name, how many of each of those you have. The reason, obviously, we have the 2 there is for what we talked about earlier, right? We have the 2 there to balance out the charge properly, because what that is basically saying is this compound is 2 sodium ions, each at +1, and 1 oxygen ion at a -2. And once again, as we talked about a second ago, that's going to give us our +2 that balances out our -2. And that is what's going to, again, give us everybody getting to that noble gas configuration. So absolutely, there is a place for prefixes. I will just give you this friendly advice that the place for prefixes should never be in the same place where there's a metal. So the way you want to remember that is if you have a metal, you should resist that urge to use a prefix because it's probably going to be wrong. So prefixes and metals don't come together in the naming aspect of it. Any questions on that there? Are you going to have a periodic table for tests? Do you haven't memorized the periodic table? Me either. I'm just asking. I haven't memorized it either. I don't know. Yes, you will get a periodic table for tests. There will be no names on it, but it'll just be formulas and stuff like that. Yeah. Well, that is the test. It's just an empty periodic table. You fill in everything you know about it. I actually knew somebody that gave that as their final exam. It was like a empty periodic table with I think just the element symbols. And it's like fill in everything about all the elements that you learned the whole semester. I'm like, I that wasn't my class. That wasn't I didn't give that. I think I would drop that class personally. It doesn't seem like a crazy. All right, let's talk about this here. So once again, type 1, whole name of the metal, IDE on the non-metal. So when we see potassium iodide, which is Ki, once again we take a look at this, and that is a metal. Iodine is a non-metal. So once again, when we always have this combination, that's going to be ionic. Once again, when a metal is involved, that is the most important thing. So we go to the periodic table, we look on group 1, and we find potassium hanging in there. And that tells us it should have a fixed +1 charge, which tells us it is a type 1 metal. And again, that's all we need for the naming. We could just go and whole name of the metal, potassium. And again, our iodine gets the IDE at the end of it and becomes potassium iodide. Just like we talked about before, when you do see the formula here of Ki, although this formula has no charge in it, because it should equal to 0, which it does. It is still made up of two ions. It is made up of a cation, that is K plus because it's group number 1, and it's made up of an anion, that is I minus. And that is why the formula is what it is, because K plus is plus 1, I minus is minus 1. So when you take plus 1 and minus 1 and put them together, it equals 0. So you just need one of each, basically, to get to that 0 that you need when you do that. Any questions on that there? All right, so why don't you try some here? Why don't you also try to write some formulas? Let me make up some names here. Let's go with sodium nitride. Let's go with let's do aluminum oxide. And let's do hydrogen bromide. All right, so we want some names here on the left, and we want some proper formulas there on the right. So take a few minutes there, see what you get. Look at the big periodic table there on the wall, or if you got one near you, it might be easier too. All right, let's take a look, see how you're doing. So we're going to start here on the left, and we're looking for names. So once again, we want to kind of identify what we're dealing with so we know how to go about naming it. Hopefully you can recognize K is potassium, which is a metal. Cl, which is chlorine, which is a nonmetal. So that's a metal, nonmetal. Once again, always an ionic situation when you have that combination. Once again, whenever a metal is involved, that is the most important thing. And here the metal is K, which is potassium. We go to the periodic table. Once again, we find K in group number 1, which means it has a fixed positive charge of plus 1. And that tells us that this is a type 1 compound. And in terms of naming, that's all you need. We're just going to go with our rule, which is the whole name of the first one, which is potassium. And the second one gets the IDE at the end of it. And instead of chlorine, it becomes chloride. So that would be potassium chloride in this case. Yeah. Again, the formula together here has no charge, but it is made up of two ions, a plus 1 for potassium because it's group 1, and a minus 1 for chloride because it's group number 7. And once again, that's why the formula is one of each, because plus 1 minus 1 gets you to 0. Question on that one? Coming to the second one, we see calcium, which is a metal, bromine, which is a nonmetal. So once again, that checks the ionic box. Metals involved. I take a look at the metal. That is calcium. I look at the periodic table. Calcium's hanging out in which group? 2. And that means that calcium has a fixed positive 2 charge. And that means, again, that checks it's a type 1 situation. We could get right to our naming. This is, again, going to be the whole name of the first positive guy, which is calcium. Second guy is going to get the IDE, and that would be calcium bromide. Am I putting a prefix with this? No, again, you don't want an X right on your paper, right? So no prefix. Once again, the reason in this particular case, right, that we have the 2 there is to balance out the charge. That's because calcium is group 2, which is a plus 2 charge. Bromide is group 7, which is a minus 1 charge, which means when we put it together, we actually need another negative charge there to balance it out. So we need not 1, but 2 of the BRs. That gives us a minus 2 to balance out the plus 2. And that is why there is a 2 in that formula, because there's 2 bromide ions present. And again, has no bearing on the actual name of it when you name it. Yeah. What's that? No prefix at all ever when a metal is involved. There is a place for prefixes. It is not here. We'll talk about where that is, but it's definitely not here. So the way you want to remember it is very simple. If there's a metal there anywhere, and it usually should be at the beginning, you should not be using a prefix ever in that name, anywhere in that name. So if you see a metal, take prefix out of your head. Don't even bother with it. You should not be using it. All right, here, this is barium, which is a metal. Hydrogen is actually a non-metal, right? Because it's hanging out over there, but it's a non-metal. And this is ionic compound. Again, barium is group number 2, which means it has a positive 2 charge. And that's going to give me barium because it's type 1. And hydrogen, because it is second here after a metal, is actually the negative version of hydrogen. And that's because the barium here is +2. Hydrogen is actually the negative 1. And once again, the reason we have the 2 down here is because if I were to put this together like this, it is not going to equal 0. I need one more negative charge there to get me to get it to equal 0. And that again gives me 2 hydrogens, which again is why we see the 2 there. 1 barium, which is why there's nothing written next to barium, which indicates that there's just one of them there. Any questions on any of those names? All right, you got the name, you want the formula, so you should also approach it the same way. So first off, I see a metal name, so that tells me it's ionic. I see nitride, which is like nitrogen, which is a nonmetal, so it's also ionic. And basically, that is a type 1 sort of arrangement. So it's an ionic compound, which means we really want to just think about the basic 2 ions that make this up. So if I went to sodium on the periodic table, it's in group number which one? Sodium's in group 1, which means sodium should have what type of charge if it's in group 1? Positive 1, right? Group 1, always positive 1. You'll never see a sodium with any other charge than +1, yeah? Now, nitride is nitrogen from the periodic table. Nitrogen is what group on the periodic table? Yeah, our group 5. And group 5 has what type of charge? -3. So it's important the number in addition to the positive negative. So these are the 2 basic ions that make up this compound. Now, as we also talked about, right, whenever we put these guys together, the charges need to equal what number? 0. In this case, do I need more of the positive or more of the negative to get to 0? Yeah, and I need a grand total of not 1, not 2, but I need 3 of them. All those guys together is going to give me a +3 to balance out that -3. And at this point, frankly, I could just count what I just did there. That's 1, 2, 3 sodiums. Positive guy goes first, 3 on the bottom right of it, and only 1 nitrogen. And you will end up with the formula there, Na3N in this case. Now I come to the next one and I see aluminum. And aluminum is a metal. Oxide is oxygen, which is a nonmetal. So again, this tells me this is an ionic compound. So I should have 2 ions. I should have a positive ion and a negative ion. In this case, I go to the periodic table. I find aluminum hanging out in which group? 3, which means what type of charge should it have? +3. Oxygen is hanging out in group number 6. So it should have what type of charge? -2. Once again, if I were to put these together, remember it goes right, +1, +2, +3, skip, -3, -2, -1, 5, 6, 7. If I were to put these together, I am not going to get to 0. I want a common number that's going to get me to 0. Simplest way to do it is multiply the 2 numbers together, right? 3 times 2 is 6, right? So to get my aluminum to 6, how many do I need? Not 1, but I need 2, all right? To get my oxygen to 6, how many do I need? 3 total, right? That gives me a -6 when you take all those together, and a +6. That's going to equal 0. Now I took 1 and 2 aluminums, which means when I write my formula, Al2 on the bottom, to tell me I have 2 aluminums. And I got 1, 2, 3 oxygens, a little O3 action. And there we go, right? The formula again has no charge added to it. Question on that? Yeah. It is. So as we talked about at the beginning there, when you look at the periodic table, if you go from group 1, 2, and 3, where aluminum is, it basically everybody in there is +1 in group 1, +2 in group 2, and +3 in group 3. Those are fixed charges that they always form. Yeah. You then skip group 4, and then you go 5, 6, and 7 above the staircase. Those are nonmetals. And they will also have fixed negative charges of -3 in group 5, -2 in group 6, and -1 in group 7. And these are kind of fixed charges. They will always make those charges. So that's how we get to the +3 for the aluminum. And then aluminum is a metal, which means it has properties that makes it want to give away its electrons. And when it loses electrons, it becomes more positive, and that's how it ends up as being a +3. Yep. Other questions? All right. Hydrogen bromide. This is a little tricky one because hydrogen is what type of metal? What type of metal? What type of element? That'd be a better question. Hydrogen is actually a non-metal, and bromine is a non-metal, actually. These are actually two non-metals together in this case. Now, we talked about hydrogen being kind of special, if you will, right? It's like the only element that can kind of be positive and negative. It's hanging out over there in group 1, right? Even though it's a non-metal and all the other non-metals are way over here. So one of the reasons why you see hydrogen way over there in group 1 is even though it's a non-metal and it does all non-metal things, a lot of times the way we name it when it's in a compound is very much like a group 1 type of guy. So in this particular case, if we have hydrogen bromide, we think of it almost like a metal, and it's going to be the positive version of hydrogen. And bromide is bromine, which is group 7, which would be the negative version of it. And in this particular case, -1 of Br, we just need one of each, and we will get HBr. Now, truth be told, this is actually not an ionic compound. It is not really two ions together. It's actually sharing electrons, but because hydrogen is kind of a unique situation, whenever you have hydrogen in front, you kind of name it and treat it like a metal, a group 1 metal, and it's only hydrogen that we do this with, no other element. So it's just kind of a special thing that happens with hydrogen. Even though, as we'll talk about when we get to bonding, those two guys are actually sharing electrons. So it's actually more of a covalent compound. The reason that is because in the gas phase, they are sharing it, which is what hydrogen bromide is. But when you kind of bubble that through water, it will actually make an acid, and it will turn that hydrogen into H plus ion, and it'll behave very much like a +1 ion. So it has a lot of characteristics that are very similar to kind of group 1 and group 1 metals. So it's kind of grouped in it when you're naming it. And in an ionic compound, if you have a hydrogen in front, you basically just call it hydrogen. By the way, if you had multiple hydrogens in front, like H2S, we would still follow the same type 1 rule, which is we would not use a prefix here in this situation either. This would still be hydrogen sulfide. So hydrogen is kind of a weird, unique one because it could kind of go both ways. It is very much in naming treated like a type 1 metal, even though it is a non-metal and even though it will still share electrons. For that sort of acid reason is why it's sort of treated like a type 1 guy. Any questions on that there? Any questions so far on what we've been talking about? Yeah. All right. We're talking about ionic compounds and we're talking about type 1 compounds. And just to let you know that sometimes people are taught a way to figure out the subscripts and the formulas and the charges by doing something like this, which is Al, say 3 plus and O2 minus. So sometimes people are taught that all you have to do is just kind of move the charge this way and this way. Or if you have the formula like this, All you have to do is kind of move the subscripts to the top to figure out the charges. And in this particular case, we would end up with Al2O3, and that would give us a calcium with a +2 charge and a Br with a -1 charge, and you would get the right answer. So sometimes people are taught sort of the switcheroo move there, like so. I will tell you, though, that it does not work 100% of the time. It's like 93% of the time. So if you're good with that, you could just blindly sort of do that. I think it's probably better just to think about like we've been doing, kind of balance out the positives and negatives. You'll always get the right answer. But again, it's very common for people to be taught just kind of move the things kind of diagonally there, and that will get you charged. And again, 90 some odd percent of the time, you'll be okay. But there definitely is a lot of situations where you will get the wrong answer if you just kind of just do that without thinking. So again, like I said, I would recommend you kind of think about it and kind of balance it out like we've been talking about. You will always get the right answer if you do it that way. All right, then let's talk about type 2 ionic compounds. So once again, type 2 is still ionic. We are still dealing with a metal and a nonmetal. And just like before, because we have a metal involved, it again is the most important thing. And with the deal on this metal is it's most likely going to have a variable positive charge. And that's going to be on the periodic table. Anybody in the transition metal region, except for, bless you, except for, as we mentioned, the zinc, cadmium, silver, those are type 1. And again, just to the right, underneath the staircase. Again, things like lead, tin, and in that sort of area of the periodic table there and underneath the staircase. Now, what is the difference here? Well, let's just say we take something like FeCl2. And the difference here is because it is obviously a metal and a non-metal and ionic, the metal is a transition metal. You can find iron right there, dead center, probably the periodic table in the transition metal region. That should tell you again that metal is in that area. That is a type 2. And what that tells you is it has a variable charge, which means you may not know what the charge is on the iron at this point. So you do have to sort of figure out perhaps what the charge is on the iron. The good news is you will always know the charge of whatever it's attached to. So in this particular case, I have an iron, and I may not know what the charge is, but I do know Cl is group number what? 7, which means Cl has what type of charge? -1. And in this particular case, there's not just one Cl, but there are 2 of them, right? So I have 2 of those Cl minuses. That gives me a grand total for my negative side of -2. And remember, right, an ionic compound needs to equal 0. So since I only have one iron, the charge on iron must be what to balance it? Yeah, it has to be a +2 in this case to balance it. So you do have to sort of figure out what the charge is in this situation, because iron, for example, could be +2, could be +3. It does depend on the situation. And it does also affect the name. The good news is we do name this very much like we name type 1. So we're going to do kind of the same type 1 move, which is, again, we're going to use the whole name of the metal. We're going to still give the nonmetal that IDE ending. But the additional thing that you have to put into the name when it is a type 2 situation is we'd use a Roman numeral in the name. And people oftentimes screw up what the Roman numeral is for. The Roman numeral is the charge, the positive charge on the metal. So if you took one metal ion by itself, what the positive charge is. So that is the positive charge on a metal ion here. It is not what a lot of people think, like how many of the metals you have. Like, Iron 3 means you have 3 irons, basically. That is not what it means. It is actually what the positive charge, if you took one of those metals out, what that positive charge is. So when we come back to our guy here that we just kind of dissected, we start with the whole name of our metal, which is iron. We have figured out that our iron in this situation is a +2, which means this now becomes Roman numeral 2, once again for the charge. And the last part of it, just like type 1, doesn't matter, I have 2 of them, it's just going to be chloride. Again, I could remember not to use a prefix here because what's in this compound? There is a metal, yeah? So metal, no prefix, yeah? So that's a good way to remember it. And that would be the proper name here, iron, Roman numeral 2. 2 because the iron has a +2 charge, and chloride just like normal. Now, you may be asking, why do we need to do this? Because if I had, say, this compound, say I had this compound here. Let's say I had FeCl3, right? This again is iron, which is a metal, and chlorine, which is a nonmetal, so it's ionic. Just like before, iron is a transition metal, which tells me it's type 2, has a variable charge. When I look at my iron, I just have one of them. I have my Cl, which is group 7, but I don't have 2 in this case. I actually have 3 of them, right? And that means I got an overall -3 charge. That means in this particular case, my iron is not rolling with a +2, but it's actually should roll with a +3 to balance it, yeah? And the name of this one would be iron Roman numeral 3 because of the charge, and chloride. I'll just kind of go underneath on an angle here. Iron Roman number 3 chloride. So the reason we have to use a Roman numeral is we have to tell people when we look at it, in this case, we're dealing with the iron with a +3 charge. And in the other case, we're dealing the iron with a +2 charge. The reason we don't need a Roman numeral on type 1 is sodium has a fixed charge. It could be no other charge but +1, which means you don't need to tell people it because it can't be anything other than what it can be, which is +1. So that's why we don't use Roman numerals with type 1 because they're fixed. There will never be anything else. But with type 2, because the metals can have a variable type of charge, depending on the situation, we actually have to tell people, hey, in this situation, it's the +1, or it's the +2 version of this metal, or the +3 version of this metal. Any questions on that? And again, transition metals, and just to the right there are the ones that can kind of do that. So why don't you give the name of that? PB is lead. What should be the proper name for this one? Take a moment. Okay, so let's take a look. So obviously PB here is lead, which is a metal. It is oxygen there, which is a nonmetal. So again, this tells us it's ionic. Lead is not a transition metal, but it is one of those ones just to the right that's underneath the staircase there at 82. And although it's not a transition metal, it can have a variable charge. So it is named like a type 2 compound. And that location tells us it's type 2. Once it tells us it's type 2, we do need to figure out what its charge is. So in this particular case, we have just one lead ion. We know that if we go to the periodic table and look at oxygen, it is group number 6, I hope, yes, which means it should have what type of charge? -2. And once again, there's not just one, but there's actually 2 of them. That is going to give me a grand total of -4 in this case. That means the lead should have what type of charge? To balance it, +4. Yeah. And that would give us a name of lead Roman numeral 4, once again for the charge, and oxide. Even though there's 2 of them, it doesn't matter. I would just mention the fact that people are very commonly taught just switch the numbers to the top. This would be a fine example of you will get the wrong name, right? Because if you just did the switcheroo, you're going to think this is +2, and that is -1 and is not. So again, before, like I mentioned, kind of doing the switcheroo of those things work 90 some odd percent of the time, but definitely not 100% of the time. So, make sure you think about it before you just kind of blindly throw it up there. I can't tell you how many people would probably write, and maybe some of you out there wrote lead 2 oxide for this instead of lead 4. Yeah. All right. There is an older way of naming, which honestly we're not going to actually use here. We will strictly use Roman numerals for type 2 compounds. But some type 2 compounds are named by historical names, and the one with the larger positive charge will end in ic, the one with the lower positive charge will end in ous. So, for example, instead of iron 2 and iron 3, they call it ferric and ferrous for iron. Instead of copper 2 and copper 1, they call it cuprous for +1 and cupric for +2. I would say iron and copper, old school names, still roll out a lot these days, even still. But for us, we will strictly roll with the Roman numerals. But if you see it, it's just sort of an older way of naming these type of compounds that have a variable charge. Here's a table from your book that gives you some of those Roman numerals. And once again, you can see the Roman numerals again correlate to the actual charge. One of the weirdest ones that you will come across in type 2 land is mercury with his Hg. And this is Hg2 plus 2. And this is Hg2 plus. Oddly, the one with all those twos, the 2 on top and the 2 on the bottom, is mercury 1. Yeah. So this is mercury. I won't write the whole name there in that room, but that's actually mercury 1. The one with only 1 2 is mercury 2. It should be down here in this area here. And that is because mercury 1 actually comes as 2 mercury 1s stuck together. And that's why there's a 2 at the bottom, because it's basically not perfectly drawn like this. It's basically 2 mercury 1 ions stuck together is how they come. And that's why there's a 2 on the bottom to indicate there's 2 of them. And because each one's +1, they add up to +2 overall, even though it's mercury 1. So how do you know which one's which? That 2 on the bottom tends to still hang around. So if you had HgO and Hg2O, which one is mercury 1? It is this one here that has the 2 still hanging out. This is Hg2 plus 2 and an O2 minus. -2 plus 2, it gives you 0. Still have the 2 on the bottom. This is Hg2 plus and O2 minus. +2 and -2 gives you 0. No 2 on the bottom there, right? So that extra 2 on the bottom tends to still stick around, and that's how you can kind of identify that it's actually the mercury 1 versus the mercury 2. Questions on that there? All right, so as we talked about before, basically same deal as type 1. The only additional thing is that Roman numeral to indicate the charge on the metal, and you do have to figure it out, but once again, you will always know the charge of whatever it's attached to that metal, so you just kind of have to work your way backwards to figure out the positive charge. All right, so why don't you give those names there on the left? Why don't you also write some of these formulas? Let's do iron, Roman numeral 3. We'll go bromide. Let's do tin to oxide. Let's do copper 1 nitride. All right, so let's do formulas here on the right, names on the left. So take a few moments there, see what you come up with. Okay, so let's take a look, see how you're doing. We'll start here, and again, always just kind of want to identify what you're dealing with when we're naming. So CO is cobalt, which is a metal. Cl is a non-metal. So once again, we know this is ionic. And when there's ionic, it involves obviously the metal is the most important thing. We just want to locate the metal there on the periodic table, right there at 27, right, in the transition metal region, which tells us most likely going to be a type 2 situation, and it has a variable charge, which means we need to figure out the charge on it. So we just want to keep it simple. We're going to start with our one cobalt, not sure what it is. Once again, we could rely upon what it's bonded to figure it out. So Cl is group 7, which as we talked about is a -1 charge, right? And in this case, we actually have 3 of them. So if you just want to draw it out, if it helps you, do it. That gives us a -3 overall negative charge. Since we know it's got to equal 0 to balance it out, since there's just one cobalt, that's got to be going with a +3 charge in this particular case to balance out the overall charge to 0. So 3 positives, 3 negatives gives you 0 in terms of charge. That's again all we had to identify here. We're going to go whole name of the metal, cobalt. Remember, our Roman numeral is not how many metals we have, but it is the positive charge. So that is cobalt Roman numeral 3. And once again, we just finish it up like we've been doing. IDE at the end for our chlorine becomes chloride. Any questions on that one there? Coming to the next one, Cu is copper. I is iodine. So that is, again, a metal, non-metal. That's ionic, checks that box. We look on the periodic table. I hope it's still 29 over there, and that is in the transition metal region. It might have changed. You never know since this morning when I looked at it earlier. So that is definitely, again, a transition metal, which tells us it is a type 2 situation. Tells us 2 things. Need to figure out the charge, and we need a Roman numeral, right? So those are the 2 things that tells us when it's type 2. So just like before, we have one copper. Iodide is group 7, which means it also has a -1 charge always. And again, in this case, to balance it out, our copper has to actually be +1 in this case, right, to balance it out. And that would give us a full name of the metal, copper, Roman numeral 1, because it is a +1 charge. And iodine becomes iodide, IDE, little copper 1 iodide. Any questions on that one there? We got tin, which is a metal. We got Br, which is a non-metal. So again, checks the ionic box. Tin is, again, not in the transition metal region, but it is one of those ones just to the right there at number 50, which is named the same way and has a variable charge. So once again, that checks the type 2 box. We're going to, again, figure out our charge. Bromine, which is group 7 on the periodic table, has a fixed charge of -1. Once again, the 4 means that we have 4 of those. By the way, the 4 does not mean we have this. There is no such thing as that, yes? So again, the 4 in that formula means we have 4 individual Br minuses that are happening ions. Because we have 4 of those, just adding that up gives us a grand total of -4. That means the tin here to balance it out has to be +4 in this case. Now we're ready to name it. Whole name of the metal, which is tin. Roman numeral 4 because of the charge. And it doesn't matter how many of those bromines we have, it's going to be bromide in this case. Tin Roman numeral 4 bromide. Any questions on any of those names there? All right, so we have the name. We want to work backwards. So one thing that we see right off the bat in all these names is they all have what? They all have a Roman numeral, which tells us it's a type 2 compound. Also tells us because it's a type 2 compound, it is a ionic compound, which means it has a metal, which is positive, right? And a non-metal, which is negative, cation, anion. So again, here, what we're looking for is just the 2 basic ions. And then all we have to do is put it together to equal 0, right? So the good news on this, when it says iron Roman numeral 3, my iron has what type of charge? +3, right? It tells you. You actually don't have to figure anything out because it tells you. You have an iron with a +3 charge because of the Roman numeral. Bromide is bromine on the periodic table. So if we look at bromine on the periodic table, it is group number 7, which means it has a minus what charge? -1. So these are, again, the 2 basic ions that make this up. Our goal here is just to get to 0. We need more of the positive or negative in this case? Negative, right? So we need not one, not two, but we need three of those negatives. And once again, if it helps you, just draw it out like this. No big deal. That -3 balance out the +3. And now we have everything we need for our formula. If you're still not sure how to write it, you just look at what you just wrote there. You have one iron, so you just put iron. And you have one, two, three of those BRs. So you put a BR with a 3 on the bottom. And again, the 3 goes to it. You end up with FeBr3. Any questions on that there? All right, tin Roman numeral 2 oxide. Again, Roman numeral tells us it's ionic, it's type 2. Also tells us the tin has a +2 charge, right? Oxide is oxygen, which is group number 6. That means oxygen should have what type of charge? -2. Yeah. So I have a +2 and a -2. I just need one of each, does that, right? That will get me to 0. So just one of each will do that up pretty good. Question on that one there. Lastly, copper 1 nitride. Copper with a Roman numeral 1 means I have a copper with a +1 charge. Nitride is nitrogen on the periodic table, which is group number 5. That has a -3. So again, putting this together, hopefully you can see that you need more of the positive guys. You need a grand total of 3 of them, right, to balance it out. That gives you a +3 charge. To balance out the -3, you have 1, 2, 3 coppers, 3 on the bottom, and you have 1 nitrogen. Looks something like that, yeah? Cu3. Yeah. Question on that? Good? Okay. I know. I was trying not to be, but maybe it is. All right. So again, I think naming is best when you keep it simple, yes? And if it helps you to kind of draw the things out like I'm doing, I would do that, to be honest with you, so you get the right answer, yeah, hopefully. Any question on type 2 compounds, yeah? All right. So just to kind of review what we've talked about so far in terms of type 1 and type 2. Type 1, whole name of metal, IDE for nonmetal. No Roman numerals needed because the metals have a fixed charge. Type 2 needs a Roman numeral because the metal has a variable charge, but still whole name of the metal and IDE at the end. All right, name all those that are not there. Good. A little decision tree, what we just talked about in case you need. Let's get to type 3 compounds. And I've been talking really bad about prefixes this whole time. This is the place for prefixes. So we finally reached where I should lay up all my prefixes I ever want to use. And it is in type 3. Now, type 3 compounds are actually different. It is basically 2 nonmetals together. And that's going to create basically a covalent bond. And we are going to have sharing of electrons here. So just like an ionic compound is always a metal and a nonmetal, when you have 2 nonmetals together, it is going to be a molecular compound that's held together by covalent bonding, and it's always going to be type 3. So type 3 is always this 2 nonmetals together. Now, because there is sharing of electrons, there actually are no ions involved here. So there's no charges involved. Nobody's got pluses or minuses. And that's because neither one of the metals want to give away their electrons. They're just going to share them. How that affects the naming is we don't have to worry about charges. We don't have to worry about balancing things. It is actually the easiest thing to name. And with that being said, it's also the one that people screw up the most because they think, well, it can't be that easy. Let me add some extras and it'll make it look more chemistry-like if I just put some extra stuff in there. So it's really just counting and picking the right prefix. So we do use prefixes here, and as we will see, we use mono for 1, di for 2. There's a table, I think, coming up. Tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, maybe some nona for 9. Could be making this up. Deca for 10. That sounds good. I'm going to stop at that name, I think, there. So, what do we do with naming these? Here's pretty much the deal. You don't have to worry about anything. Got to pick the right prefix. So, we use a prefix on the first name if necessary, if needed. And we use the whole name of the first element in the formula. And then we use a prefix on the second name. And we use the second name gets the non-metal like we've been doing with the IDE. So that's basically the way we kind of name this. So for example, if I have C and I have O, that is carbon and that is oxygen, which are two nonmetals. And that tells you it's a type 3 compound. And you should be really happy at that point because there's really nothing to figure out other than naming it correctly. Now, there are a couple rules with the prefixes that we do want to follow. The first very important rule is we do not use mono on the first name, but it's okay on the second. So that is one rule. No mono on the first name, but you're okay to use that on the second name. The other thing that happens when we have prefixes that we put in front of element names is sometimes we will get actually two vowels that back up to each other. So we will sometimes get from the prefix and the first letter of the element, we may get like two O's that back up to each other, one from the prefix, one from the element. We may get like a and an O that backs up to each other. Again, the A from the prefix, the O from like the element name. And in those situations, we typically get rid of the vowel off of the prefix, just to kind of make the name sound a little better. So let's take a look at this example, which pretty much nails everything in one sitting here with the CO. So CO is carbon and O is oxygen. Again, two nonmetals. So all we have to do is take a look at it and figure out how many of each we have. How many carbons do I have in this case? One, right? Nothing written there means there's just one carbon. And the prefix for one is mono. And obviously the first name there is carbon. Do I use mono on the first name? I don't. So no mono on this one. It's just carbon. We go now to the second element, which is oxygen. How many oxygens do I have? I have just one, right? Nothing written there, so indicates that there's one. Prefix for the second one, which is element, which is one, is mono. Can I use it on the second name? Yeah. Now, the second element is named just like we've been doing, which means instead of oxygen, it is still going to be called oxide, IDE, just like we've been doing with the IDE. And that is monoxide, yeah? Now, this, putting it together, would be carbon mono oh, that's like too many O's there for sure. I was in a rhythm and just writing O's apparently. There you go. I put the rest of it there. Monoxide there. But something else happened here. When I put my prefix together with my name, what happened? We got two vowels that backed up to each other, right? Two O's in a row. So we don't call CO carbon monoxide. We call it carbon monoxide, right? One O. So we will get rid of the O from the prefix, and this will be carbon monoxide, yeah? And that would be the proper name there for this guy. Again, there is nothing to balance, nothing charges, there are no charges, just simply pick the correct one. So if I had NO2, what should that be called? That is nitrogen, right? Which is obviously the N, which is a nonmetal. O is oxygen, which is also a nonmetal. So that tells us it's type 3. It is prefix territory. We only have one nitrogen, which means the prefix is mono, which we do not use on the first name. So we just use the whole name, which is nitrogen. We have two oxygens. Prefix for two is di. And we do use the oxide on the back end, and that would be nitrogen dioxide. Yeah. In that case, question on that there. So this is prefix all day. Yes. You also hopefully see there is no Roman numerals involved with this. You should never be mixing. Yeah. So if you find yourself doing some kind of funky chemistry name like iron 3 dioxide and you got like Roman numerals and prefixes, you're going to get an X. Yes, because that is wrong. So again, pretty much never things cross over. Roman numerals are only for type 2. Prefixes are only for type 3, which are nonmetals, and that's why you want to keep them separated. All right, so as we talked about there, I don't think it's table 5 anymore. But we kind of talked about that there. Here's a list of the prefixes, and again, we just kind of get rid of some of those awkward sort of endings. Really, it's the O, two O's together, or the A and the O. Oddly, two I's are okay. Yeah, so if you get kind of two I's, it's all good. But it's really mainly the O and the O and the A and the O that you need to kind of drop off there. And again, as we talked about before, if you had 4 oxygens, for example, we would not call it tetraoxide. Again, we have the A and the O to come together. We would get rid of the A off of the prefix and just call it tetraoxide here without the A. And there's our monoxide. We still have some common names that, again, are just named commonly. Once again, H2O is still water no matter how you tie it. Again, not dihydrogen monoxide. Yes. NH3 is ammonia, not nitrogen trihydride. All right, so these guys should go by those names. And CH4 is methane. We talked about it a second ago when we were doing type 1. Again, a reminder, if you have HBr, even though that technically is 2 nonmetals together, it is named more like a type 1 compound that we talked about earlier. And hydrogen, again, is kind of the only exception you have to kind of worry about along there. And again, that would be hydrogen bromide in that case. Kind of named similar as well. All right, why don't you try some here, see what you come up with, and let's do some names. Let's do a little dinitrogen trioxide. Let's do a carbon tetrachloride. And let's do something that doesn't exist. So let's do a trioxygen. I'm just making this up probably. Trioxygen heptabromide. Why not? Pretty sure it don't exist. All right, let's do again names on the left there and formulas on. Okay, so since we're getting to the end here, let's take a look and see how we do these. And again, since these are type 3, these really should be the quickest ones you do. You should not overthink it, okay? All right, so we'll do our normal thing. I see I, which is iodine. That's a nonmetal. O is a nonmetal. So once again, it tells us it's type 3. Don't have to figure out any type of balancing charges. Just need to pick the right prefixes. So I got 2 iodines. Prefix for two is di. Again, we use the whole name of the first element. So this would be diiodine. We have 7 for our second element there. Prefix for 7 is hepta. And the second element gets the IDE treatment. So that's going to be heptaoxide. This is a situation where we just backed up an A and an O together. So we will want to, I'll just scratch it out, get rid of the A there. So it should be diiodine, heptaoxide, no A, should be gone in that situation. Question on that one right there. Yeah. Yeah. You can use the prefix in the front. The only prefix that you cannot use on the first element is mono. Yeah, so it's specifically to mono. But you could definitely use mono on the second element, but that's the only prefix that you can't use on the first one. Yep. Other questions? All right, next one. C is carbon, nonmetal. O is oxygen, nonmetal. Type 3, I'm going to roll right into my naming. I got myself one carbon, which means I'm not going to use mono on the first name, right? And I'm just going to use the whole name of the element, which is carbon. I have two oxygens, prefix is di. And again, oxygen becomes oxide. So we have carbon dioxide in this particular case. Lastly, we have phosphorus is nonmetal, Cl, which is a nonmetal type 3. Only one phosphorus, so no mono on that first name, so that's phosphorus. Three chlorines, so prefix for three is trichloride. Yeah. Any question on any of those names? Now, probably the fastest thing you should ever do in naming is the right-hand side. So when you look at the right-hand side, on the first name there, I see dinitrogen trioxide. As soon as I see those prefixes, I know it is type 3. I don't have to worry about balancing anything. I pretty much just need to write what it says. So di means two, nitrogen is N. That means I have two nitrogens, right? Tri means three, oxide means oxygen. I have three oxygens and I'm done. I don't have to balance anything. I just basically just need to write what it says, right? Carbon, no prefix, tetrachloride, because I know from our conversation that the only place we could have a prefix ever is type 3, even though I don't see one on the first name, but I see one on the second, tells me it is a type 3 situation, right? The reason I don't see a prefix on the first name is because that means how many are there? One, because that's mono, right? We don't use it. So we know we have just one carbon, so write a C for one carbon. Tetra is the prefix for four, and chloride is Cl. So that means we have four of the Cls, right? CCl4, and we are done. Lastly, tri and hepta, prefixes tells us type 3. Tri means three, oxygen is O, so I got three of those. Hepta is 7, and bromide is Br. I got 7 of those on something that doesn't exist, but it looks nice. I got O3, Br7 in that case. Any questions on those there? Yeah. Say it one more time. Why we could have a prefix on the first name? We could have any prefix you want on the first name except mono. It's the only one you can't use. Yeah. But you can use mono on the second name, but you cannot use it on the first name. Every other prefix good for the first name. All right, we're going to lay it up.